Thank you for introducing me. I'm Laura Henderson. I'm in Sally Shrapnel's group, and I'm going to be talking about this project I've done with Rishi back there on building quantum kernels with continuous variables. And calling this a toolkit because we're just sort of showing what can be done, not what you could do experimentally necessarily. So I'm going to take the time and spend some time introducing classical kernels in the machine and what we mean by kernels, because kernels mean a million things. This is a very confusing mouse. I might just use this, if that's OK. So I'm going to introduce classical kernels in the machine learning regime, spend a little bit of time introducing quantum kernels, although you'll see that that's a pretty straightforward thing to do. And then I'm going to go into now the stellar representation of continuous variable quantum states, which you have seen a little bit about yesterday. So thank you. But I'm not introducing these right out of nowhere. Then going to give some examples on these kernels and then conclude. So what do I mean by classical kernels? So I guess to step back, we're going to sort of talk about what are some things we want machine learning to do. And one of them is image classification. So here is a sort of standard problem, or a really cute problem, is how do you know if you've got a picture of fried chicken or a poodle? There's many ways you can distinguish them. If it has a face, it's probably a dog. If it's crispy, it's probably chicken. And if you find it in a bucket, it's probably chicken, but that's not always the case. You've got this dog in a bucket here, so, you know. They're not all sufficient or necessary. So that's, some sort of basic classification problem you might want to do. But more precisely, data classification is, so if you have a set of independent, identically distributed training pairs where your xi's are some feature vector of dimension n, and with a corresponding label that's just a real number, you want to figure out a function that not only matches all of your xi's to the yi, but that can also match unseen data. So given some new x that's outside of the training pair, you want to approximate its label y. And that's your goal. So back to these images, let's make it a bit more concrete. Usually a machine learning algorithm is going to take your image and just make a vector of all your pixel values. So it's color, or it's black and white if it's just its shade. And the yi's are still the label, chicken or poodle. So there you go. You've got your vector of just pixel values. And you're going to get a 1 if there's a poodle in the image, and -1 if it's fried chicken. So one way of doing this, if you remember sort of your very simple, first-year labs or high school labs, you've got some data here, you want to find a line of best fit. And that's one way of training unseen data. So if your data is here, you could approximate the price of your house. So how do you find the line of best fit? Well, one sort of classic loss function is just the mean squared error. So your line, which goes through the origin, should be close to the correct label.
Sorry, in what city is this? These house prices are a little bit...
So this I've just taken from this website here, so okay. I don't know. Maybe some future predictive model. It did get your attention, though. So if you believe this model, you can draw a line of best fit and predict large houses and 3 million in some units. Notice it says it's just millions. So some units. And the idea is you want to minimize this loss function to get your best line. You can do the same thing for these n-dimensional vectors, but now you're taking a dot product with your weight. So your weight is now just a vector of length n and mu. And for each value of x in that vector, you're summing it with the weight. So nothing really controversial here. And that's going to give you a hyperplane of best fit. So how do you do that? Well, sort of the One of the standard ways of looking for your optimal vector that minimizes that loss function is just some gradient descent. So for some chosen learning rate, you can just update your weight iteratively by taking the gradient with respect to W. And if you've chosen your rate in an intelligent way, after infinite iterations, you're going to converge to some global minimum, which you can prove that is going to be of this form where y is now a vector of your labels, and this X matrix is just concatenating all of your vectors. And then you can take the more Penrose pseudo-inverse, which is a more generalized inverse, and you can exactly find the global minimum of your weights. So that's nice. It's a nice, well-understood problem. You can, given some data, you can find some weights that give you hyperplane of best fit. But in general, there's not going to be an effective linear mapping between your data and your labels. So the goal of machine learning, let's find a good nonlinear mapping. And one way of doing that is kernel regression. So how many people here have heard of kernel regression before? OK, so a few, but not everyone. So a kernel is, for this case, for this talk, we're just going to take, it's a positive, definite, symmetric function that maps 2 copies of your data to the real numbers. It can be complex, but let's just take it to be a real number. And so any such function that's positive, definite, and symmetric is going to correspond to an inner product in a higher dimensional Hilbert space. So where phi is your nonlinear feature map that maps your data into this Hilbert space. So all of the nonlinear stuff you're looking for is buried in phi. And what's nice is the kernel trick means you don't ever really need to know what this feature map is. It exists provided you have a positive semi-definite function. OK. So given a kernel, there's also going to be an associated reproducing kernel Hilbert space. And that's just the completion of the span of all functions that can be constructed from your kernels. Yeah?
So do you impose that it matches on 0 vector?
Sorry?
For the inner product, how do you impose that it matches when only 0?
Yeah, it's a regular inner product. So
Not on the kernels.
It's going to map exactly. So, you're asking if I have a 0 vector, do I always map it to 0? Yeah. If and only. Yeah. Yeah. You would impose that because a function is exactly, it matches. So, yeah, and actually, yeah, this is somewhat of a short talk, so feel free to interrupt me with questions. It's more fun that way. So we're going to take all linear combinations of these kernel functions on your data and take all linear combinations, complete it, and we can build a new Hilbert space, the RKHS. And that has, so it's unique to each kernel. And by the representer theorem, any function on your data also can be decomposed this way, which isn't necessarily surprising because we're looking at sort of this RKHS contains all linear combinations. So any function that lives there is can also be written in a set of linear combinations of this stuff, of the kernel function. Where again, these alphas are just real coefficients because we're mapping to the real number. Yeah?
Sorry, can you just say a bit more about what is this reproducing kernel qubit space?
Yeah. So it's
like, what is it? Can you just say a bit more like qualitatively about what it is?
Yeah. Yeah, that's fair. One way of thinking about it is it's a subspace of the dual of the Hilbert space that you've mapped your functions into. I don't know if that's helpful. If it isn't, that's fine. So what you have is you've got this mapping here, and you've got takes in 2 bits of data. So you leave this sort of empty, and you have a set of functions here, and you just take all linear combinations and complete it with Cauchy sequences, and you get a Hilbert space.
And so, yeah, they're all things that take in data points and
Yep.
data numbers.
Yep. Exactly. But so again, any function that's living in this Hilbert space will take this form. Where now the sort of left x, I mean it's symmetric, but this x here is now any future data point as well. I don't know if that helps. Great. Because this representer theorem is sort of where all the magic is. So just getting there. Now consider we want to learn this function on our data. Now possibly a nonlinear function on our data that maps data to its label. We want to minimize that. Minimize the mean squared error. So we're just going to apply that representer theorem. So that function on the data should be written as a linear combination of kernel functions. Now, if we define this new vector, so just stack up just like this. So the kj is some vector where we're just stacking up all of these functions here, all of those, numbers there, because each of these will be a number. You can write it as this, just this dot product. And that's just a nice trick. But this here looks exactly like the loss function for m-dimensional linear regression. And so we can define this Gram matrix just like we did before. We stack all those vectors up, concatenate them. And now your global minimum just is at the same point. The more Penrose pseudo-inverse of this will give you the minimum. And there you go. You've found your nonlinear function, or a nonlinear function that will map your data to its label. So sort of the big question is here, how do you find a good kernel? And that's the million-dollar question. There is no best kernel. Gaussians are pretty good. And for this, I'm going to look at quantum kernels built with CV states. Yep.
Sorry, just one more question. So this means the fit that you get,
Yeah.
the optimal fit that you get will depend on the kernel.
It will absolutely depend on the kernel. That kernel, in some sense, you've picked your nonlinear mapping, and then you're just optimizing it linearly. So the question is, what is a good K? Is that any other questions on this sort of whirlwind tour through kernels? No. All right. So kernels are not just useful for like data classification. They're used in other machine learning tasks, such as like they can be used as filters in your convolutional neural networks. They can represent attention matrices in transformer networks, training signals in generative networks. And they can be used in causal discovery. And I'm sure there's many other uses. I've seen that you can take quantum neural networks and represent them as quantum kernels. So they're quite useful even now. And then we've got some properties that we might want in our kernels depending on the context. So one might be we want it to be universal. So that means that it can precisely separate any two sets of data. Or another way of thinking about it, you can represent any smooth function as a linear combination, in the RKHS. That means that your kernel is perfectly expressive, but that you might not want it to be super expressive because exploring a really big space might make it hard to find these minima. Another property is characteristic. So if it's universal, it's guaranteed to be characteristic, but the inverse is not always true. So a characteristic kernel can be used to distinguish between probability distributions, and that's a requirement if you want to use it in causal modeling. You can embed all moments of your probability distribution in your kernel. Another thing that you might want is an easily tunable bandwidth or hyperparameter, or various hyperparameters. So for the context of this talk, what I mean by a bandwidth is it will reduce the space of learning in your Hilbert space, so just spoiler for some quantum. Rather than exploring the entire, say, block sphere, we're only exploring the top half and reducing I'm getting a bit of feedback. So reducing your Hilbert space might make it easier to find functions you want. Yeah, so key idea, make the space smaller so solutions are easier to find. And which can improve, for example, generalization bounds. So why use a quantum kernel? So it's been shown that if your data is generated by a quantum process, there's some exponential advantage in using quantum kernels. Yeah.
In the previous slide, so when you restrict the space, which is correct,
Yeah.
you still want it to be continuous because
Yeah. Yeah.
but if it's discrete, then you're not increasing.
Discrete in which sense?
Let's say I have a discrete set of points with not sphere, you're not increasing.
You will, because you are going to want a certain level of smoothness to the functions you're finding.
And that is there a framework that is okay if they're discrete.
For discrete, I have seen that. I've seen the words discrete kernels mentioned in the literature, and that's the extent of my knowledge. If your data is generated by a quantum process, you probably want to use a quantum kernel to give you some advantage. That makes sense. Look for this. It already is encoded the structure you're looking for. They have a natural SU2 structure, what qubits do. And that can provide, again, an exponential advantage in learning data with that particular group structure. Or you could, another thing you could leverage, I don't have it here, but looking for, say, coset. Like if you want to look for cosets within your structure, that's equivalent to solving the D-log problem. And so, again, if you want to leverage quantum algorithms on top of that, it makes sense to be using, again, quantum kernels. They're also more expressive than classical kernels in the sense that, so you can explore for a larger range of functions, which can be a plus or negative. Again, too expressive, you might never really find anything. But they do naturally arise in quantum information. So if you recall that a kernel, positive semi-definite, semi-definite symmetric function, is an inner product in some Hilbert space. But for classical kernels, the kernel trick means, again, you don't ever need to know what that feature map phi is. For quantum information, well, we've got quantum Hilbert space. So let's just have the data encoding map just map it into the quantum state. We have a natural inner product there. And then your overlap between your two quantum states is now your quantum kernel. So the other thing I want to say here is, unlike in the classical case, you're not actually measuring, you aren't actually explicitly calculating this kernel anymore. You're calculating in the Hilbert space, so it might be difficult to know exactly what's happening to your data. You've encoded it in some sense, and you are just looking for the statistics of this. Yeah. And this type of kernel is also called a fidelity kernel, I've been told. The actual way you would get these statistics out are going to be architecture dependent. So let's look. What do we want? Quantum kernels are highly expressive, as I mentioned, but that can make learning very difficult. Again, you're going to have a huge space to explore, function space to explore. A bandwidth may help that by reducing the amount of space you're looking at. Again, like classic kernels, the best choice of kernel is going to be problem specific. You're probably going to want to look for underlying structure within your data to exploit. So again, as we're looking for the best choice of kernels, there's been a lot of work on qubits and circuit models, but we're looking for sort of new building blocks, and there's been little work up until now that's been done on CV quantum kernels. There's a few papers that I can point you to later. But this is one of the first work that's been done for general CV kernels. When you're looking at, again, qubits and circuits, there's no sort of general closed form expression. It's a bunch of matrix multiplication if you wrote down a general form. So that might be difficult to sort of come up with what you're expecting to see. You first need to specify the gate structure, and you're usually very limited by the architecture on how you can tune things. And so that's also going to make it difficult to see in general what will happen to that encoded data. So as I said, our result, we have the closed form of a general CV quantum kernel with a bit of an asterisk beside that, because this is only for finite stellar rank. So what is stellar rank? So the stellar representation of, or the holomorphic representations of continuous variable quantum states. So we take the Siegel-Bargmann representation, represents continuous variable quantum states as a holomorphic function. So that's everywhere differentiable on the complex plane. So there are quite a few advantages of using this representation. So one is quantum operations on these states will map one holomorphic function to another holomorphic function. So it's easy to track encoding in that sense. You're always living just as you're just tracking what happens to your holomorphic functions. Inner products are easy to calculate. It's just a complex integral or a series of complex integrals. The number of zeros of your holomorphic function, they're going to provide a natural measure of quantumness through the stellar rank. And photons are pretty easy to produce, so they're fast and cheap. So more precisely, the Siegel-Bargmann space is the set of all bounded holomorphic functions, so bound with respect to the exponential measure. And for a single mode quantum state, you can decompose it into the Fock basis and then represent it exactly as this holomorphic function here. So you've got your coefficients end up over here. And so all of your all of your finite rank quantum states, so just ones that have a finite number of zeros, are always represented as a Gaussian times a polynomial. And we're going to call those stellar functions. So the stellar hierarchy, I've mentioned the stellar rank. So n, for the rest of this talk, is always going to denotate the stellar rank of your CV quantum state. It's the number of zeros of your stellar function. One way of increasing that is you start from the Gaussian and you just apply creation operations to just climb the stellar ladder. The larger the value of n, the more quantum a state is. So n equals 0 are Gaussian states, which can be classically simulated. So what I mean by more quantum is, in general, as your stellar rank increases, it's going to take exponential time to classically simulate these operations in states. And again, that's occurs for a generic CV quantum state. If it's separable in certain ways, it can be much simpler to simulate. So I've been mentioning again finite. So states with stellar rank of infinity sort of lie outside the stellar hierarchy in the sense that infinity doesn't mean infinitely difficult to simulate. The stellar hierarchy is only robust for finite n. But if you have a state such as a GKP or cat state that has infinite stellar rank, you can approximate it to arbitrary precision by states of a finite rank. So they're always within, you can make them epsilon in trace distance. And then finally, Gaussian operations are, by definition, do not change the stellar rank. So, of course, the Siegel-Bargmann space is a Hilbert space. They're bounded, and again, as I alluded to before, if you've got an M-mode stellar functions, you can just calculate the inner product through this complex integral. And it's a complex integral of states of Gaussians and polynomials, or a product of a Gaussian and a polynomial, and you can find that analytically. So we're just going to define, again, our CV quantum kernel as a fidelity kernel, like that. So, before I move on to now sort of more specific examples, are there any questions about this stuff? Okay. So now we're going to write down a couple of examples of these kernels. So sort of the simplest thing that we could think to write down is a single mode displaced Fock state. So we're just going to encode the data, which is just two real variables, into a single mode state by simply applying your displacement operator to a Fock state, where now not bold alpha is a complex number. All of your stellar rank is encoded in the initial Fock state. Because the displacement operator is Gaussian, it's not going to change your stellar rank. So we're just going to do that. A single mode Fock state is simply this function here. The displacement operator is going to apply that Gaussian and shift your origin. So our encoded state is simply this function here. And our quantum kernel is the inner product of those two states, or this integral. Yeah?
So in the standard rank, usually the polynomial part and the Gaussian part also is squeezing.
Yeah.
Is there a reason you only chose displacement and squeezing?
Because the squeezing can give you one number, and it mathematically looked worse than a displacement that can give you two.
So it's a sort of outcome that, okay, you learning these things, this behaves better than the squeeze, if you ask me.
I'm not sure if you were actually doing it in an actual lab, but when I was grinding through these calculations, this was a nicer integral to do and gave you two numbers instead of one. So this is an integral you can do analytically. I'm not going to show it here, but it's got some pretty nice properties. It shouldn't be too surprising that your now kernel is also the product of a Gaussian and a polynomial of degree 4n. So your complexity goes from n to 4n. Again, not really surprising because you get 1n from each of those, and then you square it to get to 4n. It's translation invariant, so you can just write it as the difference between your two vectors. And it's rotation invariant, and by rotation I mean this is just your rotation on the two-dimensional plane. So from 1, 2, and 3, you can actually write your kernel as a function of the magnitude squared of the difference in your vector, between your vectors. And that's nice because you can simply take that Fourier transform and find that it's a Gaussian times a non-negative polynomial, which is nice because that means that it's a characteristic kernel. And if you wanted, you could use it for causal discovery. You can embed probability distributions into this kernel. So it's quite useful. And this is what it looks like. So what I've done is just plotted the function for various values of n, 2, 4, 8, 0, 2, 4, and 8. The larger value in n has a larger envelope. So what I mean by that is you can have further distances and still have sort of non-exponentially suppressed values. And larger values of n have more local maxima. That's not surprising. Larger value of n is higher degree of polynomial. Now the average of each of those maxima increases with increasing n. So you're going to have, if you imagine going, n is 100, you're probably going to have just a bunch of almost indistinguishable maxima. So there will be a point where you have too high of a value of n, and you're not going to get much of information at all. And we've taken that kernel and done some verification simulations. So we just want to demonstrate that the displaced Fock state kernel can classify data. We're not looking to compare it really to anything, just can it classify data. So if you recall, it's a radial kernel, so we're going to choose radial data. We're going to stack the deck to help us as much as possible. In data set 2, we've added a bit more complexity by flipping the labels of your data above the x-axis. And there's noise in all of them, a small amount of noise in data set 1 and 2, and then about as much noise as you can get before you have complete chaos in data set 3. And what have we shown? So this figure here is showing the decision boundaries and the test data across a kernel of n equals 1, n equals 2, n equals 3. This is an untuned Gaussian, and then a Gaussian that's been tuned through Bayesian optimization. And as you increase the stellar rank, the displaced Fock state kernel can classify data with no hyperparameter tuning. The n equals 1 is about 60%, but n equals 2 and 3 are above 90. Those require no hyperparameter tuning, but the classical Gaussian needs computationally expensive hyperparameter tuning to obtain the same accuracy. You see something similar in data set 2, so the extra complexity. It does make things a bit more challenging. You need to go to n equals 3. N equals 1 isn't shown, but you need to go to n equals 3 before you start to really see accuracy above 90%. So it is a harder classification task. You see the same, so the accuracy again is increasing with stellar rank. And again, you need the hyperparameter tuning in the Gaussian to get similar accuracy. So we also wanted to look at this bandwidth tuning. So if you recall, it's interpreted as a reduction of the Hilbert space that we're going to explore. So we're going to do this in phase space by just reducing the size of the displacement, which corresponds to rescaling the data. So first, to sort of see what it does to the function, we're just going to look at a uniform distribution of data and look at its kernel value. So due to the Gaussian, as I said before, if you've got a distance way out here, it's going to be exponentially suppressed. And this is for n equals 4. In the n equals 4 case, it's showing up for if the distance between alpha and beta is more than about 5. And that's going to correspond to they're going to be indistinguishable and there's any noise in your measurement for values out here. You're not going to be able to tell if you're here or here. As you're decreasing the bandwidth, you're basically moving the data further inside that envelope. So now you can actually distinguish values out here. And so you do have an effective loss in stellar rank if you see you've got sort of 4 maxima here instead of 5. So you're losing an effective stellar rank, but there's some loss of quantum advantage. But of course, the stellar rank of the function's not changing. It's the same function. You're just reducing where your data is sitting. And if you make your bandwidth too small, you have a Gaussian again. It's classically simulable. And again, if you want to take C greater than 1, you now sort of lose the stuff sort of further in is suppressed. So now you're cutting off data. You're not going to see anything. If the distance is greater than 4. But that's going to put more resolution in your small values, which we do show is going to be useful if your model is underfit. So again, turning back to your hyperparameter tuning, we're going to focus on the n equals 1 kernel, the one that had poor accuracy, and increase your bandwidth to focus on the low energy structure. And you can see that as you increase your bandwidth, with no bandwidth tuning, you're at 60%, and then increasing it 80%, 90%. If you go too far, you start to really be overfit. But we found that a bandwidth of 1.5 is about optimal. Of course, that 1.5 is just checking a few values, no extensive search. On the flip side, if you've got very noisy data, again, this is on data set 3, that's about as noisy as you can get before it's just randomly guessing. The n equals 3 kernel has poor accuracy, they all do. But if you decrease the bandwidth, if you actually decrease the bandwidth, you do get slightly improved accuracy. So from 60 to 63%. If you decrease it too small, then your kernel is effectively, looks like that untuned Gaussian, just a blob sitting in the center. And you also see through this that in this figure here and this figure here, you're comparing an n equals 1 kernel, n equals 3 kernel to an n equals 1 kernel, and sort of the structure looks similar with that bandwidth, indicating again that loss of effective stellar rank. So sort of the summary of all of those simulations. The single mode displaced Fock state kernel can classify data, but we pick data that matches the structure of the kernel to make it as easy as possible. So if there's little noise, the hyperparameter tuning isn't necessary. And with no hyperparameter tuning on data with little noise, its accuracy is comparable to a Gaussian kernel tuned via Bayesian optimization. A Gaussian kernel is the ideal, is sort of the universal kernel. Everyone throws a Gaussian at learning tasks. And that's just sort of showing, again, that it can learn, not necessarily better. Increasing the bandwidth parameter will improve accuracy in an underfit model, and decreasing the bandwidth will improve learning on very noisy data. So that's what we showed. So another example is if we want to encode another Gaussian operation is this phase shift operation, and that's going to allow us to encode a third parameter in our data. The phase shift operation acts on your holomorphic function by just adding a phase. And it can actually be used to encode 3 numbers. These two, again, are real numbers, and this is phi. Script phi is just a compact variable. So your encoded state is going to look like this. And we can take the inner product or the integral, if you want, and calculate what the calculate what the quantum kernel is. There's an analytic expression for it. But just showing you sort of what it looks like. So rather than showing those 2D models, this kernel is not shift invariant, so it actually depends on 5 parameters. Sort of the 2 real numbers from alpha 1, alpha 2, beta 1, beta 2, and then the phase difference. Most of the complexity is going to come into the phase difference. So as you increase the phase difference from here to here, your kernel sort of looks less squished, becomes a circle, and then sort of starts to squish again. So sort of the takeaway from this is this is for n equals 5. Again, you see that structure of there's sort of 6 maxima and 5 minima. You have that overall sort of Gaussian that's exponentially suppressing your data away from your sort of central maxima here. So again, you see that polynomial and Gaussian part of your data. Again, the majority of your complexity comes from this phase difference. So that's going to set the eccentricity of your envelope, and you see that sort of similar behavior, whether or not you're plotting against alpha 1, beta 1, or alpha 2, beta 1, or alpha 2, beta 1. All of that sees sort of a similar qualitative behavior. And as I said, it's not a translation invariant kernel, so proving if it's characteristic is a lot more non-trivial, and I don't quite know how to do that. So I can't say with certainty that this is a characteristic kernel. But that's just another example. The big takeaways are you see that Gaussian and polynomial and how that sort of seems to be universal among these kernels. So what's the most general thing that you can write down? If you've got an M-mode holomorphic function of stellar rank n is always going to take this form. You've got sort of your Gaussian up here, your generalized Gaussian part here, and a generalized polynomial over here, where your data is encoded through some set of operations into your matrix, into the matrix A, the vector B, and your complex numbers C and beta. And you can absolutely calculate this quantum kernel by taking, and once you grind through all of the complex integrals, this is the most general CB quantum kernel you can have for finite stellar rank. These little A, B, and Ds are recursively defined and depend on your matrix A's and your vectors B. R is recursively defined. U and G are recursively defined. But that doesn't matter because you still have your Gaussian there, It's still in the form of a Gaussian, and from that you can look at how to implement a bandwidth by tuning your initial encoding. And you've got your polynomial here, which is of degree, for the inner product, it's of degree 2n, your kernels of degree 4n, and depend on your components of your matrices. And as you saw sort of in the two more simpler examples, you really do see that Gaussian suppression and the polynomial maxima. And what about, so I've been only talking about finite stellar rank, not infinite stellar rank, which is, I mean, we care about GKP states quite a bit. So how will those fit into this? If you recall, again, for pure states, you can look at the overlap between a stellar state of infinite stellar rank psi and finite stellar rank f, and that can be bounded by epsilon squared. So therefore, we've proven that all kernels generated by states of infinite stellar rank can be approximated arbitrarily well, so you can make this smaller and smaller, and you can actually reduce the distance between your two kernels by epsilon. So, sorry, if your state of infinite stellar rank is epsilon close to a state of finite stellar rank, then the kernels that are generated by those states are going to be within epsilon of each other. So if all continuous variable functions are at least order epsilon away from the product of a Gaussian and a polynomial. So I'm sure I've got quite a bit of time left. So hopefully we can have a discussion, but sort of the big takeaways of this talk is stellar representation provides a natural measure of quantumness of CV states, which lead to a measure of quantumness of CV quantum kernels. Again, stellar rank of n gives you a quantum kernel of stellar rank of 4n. The inner product of these states are an integral. They can be easily calculated just as integrals over complex planes. So we can get we have gotten a closed form of these states, which are always, at least for finite stellar rank, always the product of a Gaussian and a polynomial. The polynomial is going to say something about the complexity to classically simulate, and the Gaussian part is going to we can use to lead to intuition about hyperparameter tuning. In the single mode displaced Fock state kernel, it's a characteristic kernel, and we used it to classify annular data. So where to go next is, we've got this closed form expression, so we want to maybe we're interested in exploring questions about expressibility and generalizability, and in particular looking at exponential concentration and where that happens. None of these, there is no noise in anything I wrote down, and noise is, I believe, scales also exponentially in the stellar rank, so perhaps that's going to wash out any quantum advantage you have, or that's even more likely going to be noise dependent on your noise model. And really ideally, we want to implement a simple CV kernel experimentally. If anyone has any ideas, please come talk to us. We are lacking in the experimental expertise, so. We'd love to discuss ways of implementing a simple CV quantum kernel. So thanks.
Okay, we have some time for questions.
So if you found like a nice analytic expression for computing those inner products, how do you get a quantum advantage?
So these, so some of the quantum advantage is going to be in calculating these betas there. So you can absolutely write down, like this is something you can easily write down, but if I want to look at how to implement them in a lab, this is like actually calculating sort of the gates or the operations that give these is going to be incredibly difficult. I mean, we know that, so actually simulating the physics there is going to be quite difficult. And then now this might just be my lack of experience with complex integration, but this general kernel here this is nested. These are nested sums. And they're recursively defined. So just calculating this part is also exponentially difficult because everything here, all the gammas, r's, all G's, all of this is calculated recursively.
I actually have a question for this.
Yeah.
So if you look at this most general kernel, do you have any intuition like which, like if I give you a problem and you know a bit about the problem, like some symmetry, like how to make a good kernel out of this general, so going
that's sort of next is what I'm thinking about. I saw a paper, and I've only read the abstract of it, so this I could be completely wrong here, but it looks like stochastic processes or some subset of stochastic processes also have holomorphic representations. So presumably you're going to want matching in the set of encoding.
Yes.
If you put noise in, let's say it was Gaussian,
Yeah.
and no star, it doesn't increase,
Yeah.
but it might decrease.
Yeah.
And that's, if you want to fit to that, that's a discrete jump in the star parameter. Is that,
Yeah.
continuous fitting, is that getting in the way of that?
I'm not really sure at all about that because we haven't thought about noise at all. But presumably it would be, you'd put in the function at the encoding stage most likely and say, okay, so you've got encoding and then you're going to modify it and then you take your inner product. But we've not considered noise at all.
Do we have more questions? Yeah.
When you refer to Stell rank as a measure of quantification,
Yeah.
are you just speaking about the difficulty of simulating it classically, or are there other properties of those states which link to that?
So what I'm speaking of, I'm just going to flash the reference so that you can look, write that down as well. So So what I mean is specifically this. So this is a strong simulability criteria, so it's from this reference here. And through that strong simulability, it's basically the difficulty to simulate on it classically.
Are there more questions? If not, please enjoy the sunshine because tomorrow, starting tomorrow, it should rain. So enjoy the weather, and we will see each other at 9:30 tomorrow.